got on my mind that today we have the lab.
Oh, yeah. For sure.
I'm using. I decided to go with something that's kind of a hyperfixation right now, time crystals.
I'm not too familiar with this topic, but as long as you can relate it to chemistry.
It's quantum mechanics, mostly.
Can you relate it to chemistry? Like, what kind of materials do they use?
I believe they're using protons and using high-powered lasers to create oscillations in their spin to create any phase of matter. But I can also, I think thorium might be able, lifter reactors might be a lot easier to relate to chem. But I thought this was cool.
Yeah, it's cool. It's just very dense, and I worry, like, I just don't know, like, what you're gonna write about necessarily. But they do have, I'm trying to think, there's like single molecule magnets is kind of related to this. There's also like quantum crystal things.
That's exactly
people
what
are.
that is.
Yeah, I mean, this may be appropriate. I would just have to read it in more detail. But yeah, I'd want to talk more about like the material that they're using to create all these spin states, and that might be interesting. At least that's like the approach that I want to see.
Okay.
Is just like more of the materials, like what kind of materials.
Instead of the like quantum mechanics.
Yeah, I mean, that's
physics
just
side
like
to it.
super dense too.
Yeah.
And, yeah.
And weird.
Yeah, but if you could talk like about the materials that
Right.
are going into it, then that might be a little bit easier, and then also chemistry relatable.
Yeah. Or also like the how they're having to super cool these quantum computers because they have to be at almost absolute zero to have the entanglement work. It's very interesting stuff.
Yeah, so you could talk about that too with like superconducting. That might be a easier way to relate it to chemistry as well, because then you can talk about like why they have to cool it and what that does to the band gap. Because you just want to be able to put that in some sort of simple terms that you could write a paper over too.
Cool. Okay.
So
Yeah.
I just don't want you to pick a super hard topic for yourself.
Yeah. I really like the quantum computers. It's kind of a thing. It's a at-home interest. So, yeah.
Hey, Miss Lisa.
How's it going?
It's okay. So, I was confused on how to like find the concentration decision. Is this difficult? Like, how do you punch the finger? And the volume. When you just plus, and I've turned it to liters, and I plused it the 98.8.
Yeah, so that, I mean, that looks like roughly the right steps, because you just calculate moles and then do your new concentration. But then, okay, cool, you plugged it into.
Yeah, but I was confused because this was on the, for the 0 NaOH added, so what do I put there? Just nothing? Because like that doesn't work. Like it doesn't.
So then you'll just you might have to use the ice table first initially.
Oh, for the first
yeah.
one.
So just do the ice initially to figure out how much is in equilibrium. And then after the ice, then you should be able to use HH for the rest of them.
I tried to use it for this one, and I got like a feature like 7.11. So I don't know if I feel like I'm missing something. For the second one, for just I1. Like, probably hard to understand my stuff on here.
Yeah, let's take a look at it after class, because
Okay.
we're like at
Oh,
time.
okay.
But yeah, we can check your math and go through it. Nice.
You know, we're kind of extra.
Did you obtain your own algae?
He did. We're still gonna use the balls though.
You're an American hero. Oh, I said you're an American hero for getting algae. Because I was telling Nicole to buy algae, because another group also wanted algae, but I don't think it happened.
There's more. I got it.
All right. Where did Nikki go? Where'd the rest of your class go? Well, I know some people are sick, but I know not that many people, at least not that many people emailed me. All right, so let's just go over a few announcements. So don't forget the permission slips for the field trip, or the waivers, I mean. So waivers for Oregon Caves. So please take them, fill them, return them ASAP, just so we have them for my records. And then, of course, just let me know if you need more materials. So today in lab, we'll be preparing for our Earth Day project. And some of you have been emailing me back and forth. I was going to inform the Dewar people there were Dewar issues, but the Sierra and Cassandra were doing liquid nitrogen, and I asked Grants Pass to send me over the large Dewar, and they sent over the same size Dewar that we have. So, yeah. But I think Nicole is still going to get a small amount of liquid nitrogen, hoping to have large amounts of liquid nitrogen. We have poster boards too, so that'll be available. And then we can discuss whatever y'all need. There's also red cabbage as a backup emergency plan for people. All right, any questions about anything before we get started? All right, so let's finish up this last bit of the chapter, and then we may dive into the next chapter as well. All right, so we have the last bit of this chapter is also this concept called complex ion formation. And so transition metals tend to be good Lewis acids. And so that means that they often bond to one or more water molecules to form a hydrated ion. And water serves as the Lewis base, donating electron pairs to form coordinate covalent bonds. So here we have our silver metal, and it just coordinates with some equivalents of water. And so it just coordinate, right? The oxygen has our electron pairs, so it's going to be donating 2 of those to the silver. I'll draw out 2 of them. So just keeping track of our lone pairs. So, right, oxygen has 2 lone pairs in water, and then one of those lone pairs is then donating to silver or whatever metal it is coordinated to. And so ions that form by combining with a cation with several anions or neutron molecules are called complex ions. And so the fun thing about this is often they can come in different colors too, depending on what's coordinated to them, so that makes them fun to study. And so attached ions and molecules are called ligands, and that's just like anything that is attached to a metal, some sort of organic. So water could be a ligand. There's also like ammonia is a common one, or CO. And so then, similarly to how we've been quantifying everything with this relationship, we can kind of do the same thing, except with this Kf formation constant. And so now we have this reaction between an ion and ligands to form a complex ion. It's called a complex ion formation reaction. So silver, and then now in this case, we're using ammonia as our ligand to attach. And so same thing, right? Nitrogen has those two lone pairs. And so that's getting donated to now the silver in this case. I'm just drawing it like this to emphasize that nitrogen is supplying all the electrons in that bond. But now we can quantify this. So same sort of relationship like we had before. So everything is in solution. And so general expression, right, products over reactants. And so in this case, right, we're looking at our complex ion, so our silver diamine species here over whatever is left, so our non-complex silver and free ammonia in solution. And so then you would be given a table of formation constants. And so most of them are relatively high in their exponents. So this one is a little lower, this cadmium tetrabromide complex. But otherwise, generally they're pretty favorable. So there's these cobalt amine complexes. Oops. So that's fairly favorable. I was going to pull up. All right. While the internet loads, I was trying to show some examples, but let's look at this problem. And so now we have our scenario. So we mix 200 milliliters sample of a solution that is 1.5 times 10 to the negative third molarity and copper nitrate. And we're mixing that with a 250 milliliter sample of solution that is 0.2 molarity in ammonia. So after the solution reaches equilibrium, what concentration of copper 2+ remains? And so just try to think about how we might set this up, thinking of everything we've done before, all the ice tables.
Does the copper nitrate dissociate for the in solution?
Yes, so that would be soluble, so that's your source of copper. So we'll go over what you did in a second, but I was just trying to show you Werner's complexes and some of the work that's been done on these coordinated compounds. And so Werner's complexes have kind of this general structure. And so he was playing around with different equivalents and basically also kind of discovering how they coordinated. And so it was also significant in that he was able to determine the geometry, but then it was fun chemistry, since you notice all these different species have very distinct colors. So you could easily tell as you put different amounts of ammonia on there, kind of what the color is, and then able to track that down. That's a whole another section too. You could dive into Werner's complexes. All right, so let's see how this is looking. So did we at least start off by kind of writing our reaction down? And then we could also see, well, we have our basic concept here. Well, we're mixing copper and ammonia. So then we can look at our formation constant chart. And so what complex involves copper and ammonia that we are going to be interested in looking at? No? Yeah, or you could call it like tetraammonia. All these are awkward to name as well because they would need a counter ions technically, since you have, right, this is a 2+ charge on it, so then you would have some sort of what's called outer sphere chloride ions or something hanging about. But yeah, basically, right, you just want to identify the species. So this copper tetraammonia species. And so we can start by just writing out our general reaction. So that means we're looking at copper 2+ plus 4 equivalents of ammonia to give us that copper ammonia species. And so then what's the next step here? So we have our reaction, and then what do we need to do for our I, our initial conditions here? So let's find moles of everything. And so let me just bust out my calculator. So 0.2 times our molarity. So how many moles of copper do we start with?
3 times 10 to the negative 4 moles copper.
So 3 times 10 to the negative 4, or that would be what, 0.3, excuse me, millimoles. And then how many moles of ammonia did we start with? So 0.25. So how many moles of ammonia? So 50 millimoles, 0.05 moles. And so far 0, since we need to calculate that. And so now what's going to be our change for all of these?
So all the copper is going to react with ammonia?
Well, that's what we'll have to set up, right, our equilibrium expression. So you're on the right track, so let's put minus x, right? Well, some of it's going to be reacting. We don't know how much. Our KF is going to tell us how much. So this will be minus x, and that will be plus x. And then what about my ammonia here? Minus, would it be x or? Yeah, so 4x. That's a little tricky since we need 4 equivalents of our ammonia to make 1 equivalent of our copper complex species. And so now we have our equilibrium values. And so I think most of you are seeing where this is going. And so we said our KF and our species that we were interested in is this 1.7 times 10 to the 13. And then let's just rewrite what that KF means. So generally, products over reactants. So that's going to be our copper tetraammonia species. So how much of that divided by our reactant. So now our new amount and so now we need to solve or, so there's kind of two different ways here, and I think this will go back to what you had said is, does all the copper react? And so now looking at this KF here, and looking at the math, so this may be kind of tricky to solve. So looking, so now we're at 1.7 times 10 to the 13 is equal to x over 3 times 10 to the negative 4 minus x times 0.05 minus 4x. So we could try to solve for this. Or the other thing is you can also just assume that all your copper is going to be consumed since there's just a tiny amount. But let's ask Wolfram alpha to solve it and see how it compares. So I'm just going to plug it in. Oops. X divided by
Tungsten. In this case, is wolfram like the two animals, or is it the Latin name for tungsten?
Oh, I don't know anything about the name. Ah, okay. Let's see if I at least plugged it in correctly. So, all right, plugged it in correctly. I'm just making sure Wolfram alpha interpreted. Oh, I forgot the 4x, sorry. 4x. Okay. That's what we plugged in. Blah, blah, blah. And then it solves for us. And so we get two solutions for x, potentially. And so notice, obviously this one is too large. So that wouldn't work since our copper minus this answer would give us a negative answer. But then if we look at our other solution, well, this answer is the same as our copper one. And so it turns out, yes, you were right in making our assumption. So with our KF being so large and amount of copper being small, you can also just assume that all your copper forms that copper tetraammonia species. But I did want to prove that if you solved it algebraically, I know that's a little nasty looking, but you could probably just use, I don't know if you can easily solve it with the quadratic. Yeah, that's what I figured. Okay, sorry, I think you're ahead of me for a second. So then, what are we asking? So what concentration of copper remains? Probably almost nothing. So let's plug this in. And so now let's go back to our equilibrium. So now we assume that our 3 times 10 to the negative 4 moles of copper were fully converted. So that means we have 3 times 10 to the negative 4 moles of our copper complex. And then, let's see, so how much ammonia then is left? So then we need to figure out how much ammonia is left. So 0.05 minus going to be times 4 though, right, since we needed 4 equivalents. Oh, and I didn't plug that in right. Blind. Where's the insert button? Oh, there it is. And I didn't do that right. Okay. Do we get this for amount of ammonia remaining? So 0.0488 moles of ammonia. And so now if we want to get a better answer to, well, what concentration of copper do we have at equilibrium, we can plug it into our KF, except, so now we need to calculate, we need molarity though. Of our copper ammonia species, so we have to convert that back to molarity. So what's our total volume? So we have 450 mils total. Let's get our new molarity, and we'll plug everything back into our KF to kind of get a better answer then for copper. So then 3, oops. So then I have like 6.66 times 10 to the negative 4th molarity of copper. Oh, 6. And then ammonia, so that's going to be, let's take our 0.0488 divided by the total volume. So like 0.108 molarity or something for ammonia. And now we're trying to kind of resolve our copper to see how much is left in our tiny amount. And so now we can plug everything in. 0.108, and then we're just going to leave X for our copper species. So then let me know what you get for X. Should we get an answer for X? Did you get same order of magnitude at least? Make sure I plugged everything in as well. So everybody got this, or something close? Awesome. So tiny amount. And so now we end up, so 3.6 times 10 to the negative 16 roughly, molarity for copper. And again, that's just telling us, right, an extremely insignificant amount of copper is then left in solution. Any questions about this one? And so again, kind of the opposite thing. So again, you'll see all these complex formations are pretty high. So for the most part, if you have, a small amount of your beginning metal or whatever, then you can just assume that all of it is going to equilibrium. So kind of how we're able to make that equilibrium curve with the last quarter with the iron thiocyanate complex, where we just assumed that everything went and made the complex. So same sort of scenario here. And then obviously when you can't assume, then you can always plug into Wolfram Alpha or your calculator if the algebra gets too tricky and you can't figure out what assumptions to make. All right, let's look at the last little bit of this chapter. And so now we're looking at the effect of complex ion formation on solubility. So the solubility of an ionic compound that contains a metal cation that forms a complex ion increases in the presence of aqueous ligands. And so let's look at this reaction here. Oops. And so we're looking at this formation. So we have both this dissociation of silver. So we have our silver chloride, of course, dissociates to silver and chloride. But like we looked at on Tuesday, this has a pretty small KSP. So it's not very soluble. But then, what happens then if we add ammonia to our solution? And so the next step would be to figure out, well, what is ammonia reacting with? And so in this case, right, ammonia is reacting with one of our products of our solubilization reaction. So it's pulling out silver, and so that silver goes on to react with ammonia to make our, of course, complex ion. But all that means in practice is if you wanted to have silver chloride and kind of make it more soluble, one trick you could do is add ammonia to that mixture, right? And that would make it more soluble since you're making a new species. And so that's what's shown in this picture here. So we're just starting off with a bunch of silver chloride at the bottom. So that's what it would look like. Again, very low solubility. Then you add ammonia to it, and the reason why it clears up is now you've made a new soluble species in solution, your silver ammonia species. So questions about this little scenario so far? So again, thinking about Le Chatelier's principle. And so looking at these metal hydroxides, so these can also be kind of confusing if you start looking at the chemistry of them. And so many metal hydroxides are insoluble, and of course metal hydroxides become more soluble in acidic solutions. We saw that on Tuesday, so of course the hydroxide reacts with your acidic solution, and it obviously removes OH by reacting with it. But then we also find that some metal hydroxides can become more soluble in basic solutions, which seems confusing. But that's because that these ions can also act as a Lewis base and form a complex ion. And so again, we have this term amphoteric, so like aluminum metals too, so like aluminum hydroxide species tend to be amphoteric since they can coordinate both water. And so other amphoteric hydroxides are going to be chromium, zinc, lead, and I think that's antimony. And so let's look at more how this works, or some of the reactions that can go on. So if we look at aluminum 3+ here, so it starts off, so this is just an octahedral complex, and so again we have water coordinated. So that would look something like that, with water everywhere.
Is that just because water's polar?
So water can act as a ligand again in this case, so of course water, I mean, yes, polarity helps, but it also has the 2 lone pairs, so then one of those electrons is going to be involved in bonding to the aluminum. Make sure I drew that. 1, 2, 3, 4, 5, 6. And so now we're here. So we have our species. And then, well, let's see, well, how does it form an acidic solution? And so if it's sitting here in water, and so, right, we're just aluminum hydroxide plus water. And so it can make an acidic solution because now one of these waters can go ahead and react with one of these complex species and pull off one of its hydrogens. And of course that would make, I apologize for writing this all over the place, and of course that gives us our hydronium then. So now we're saying, okay, this can make an acidic solution, and then that just pops off one of the hydrogens, so now it's still coordinated as just a hydroxide, and then obviously all the other waters are there. And so if we look at this, so now if we add OH, this drives the equilibrium to the right and continues to remove H plus from the molecules. So now looking at this equilibrium, so it made an acidic solution. So if we add hydroxide, right, that removes this hydronium. So that means it just keeps driving this. And so we started with 5 equivalents of water now, 1 equivalent of hydroxide coordinated to the aluminum. Now if we add basic conditions, now that's just going to pull off subsequent H plus ions. So now we go from 5 to 4 equivalents of water, 2 equivalents of hydroxide. And of course that forms water in solution, so doing a neutralization from one of these H's on that was formerly on the water on aluminum. Now it's reacting to just form water. And then you can do that again, right? So if you, depending on how many moles you have, so then it would go from 4 to now 3 waters complex, and then 3 hydroxides complex. So kind of interesting chemistry there. And so again, it would be acidic and all complex as water. And then as you go more basic, then you get more and more hydroxides complexed on there. Any questions about this bit here? Let's look at the homework. So homework's still up front. So was there anything on the homework that stood out and looked difficult? Questions?
On the second page, how do we find what ion to use to separate?
This one, the calcium from the barium?
Yeah.
So this is a good one. So let's see. Let's go back to our notes for a second. What happened to all the KSBs? Let's see. So we care about barium and calcium. So if we just look at this one, let's see if there's enough. Yeah, I think there should be enough. So looking at this table, kind of what are our choices to separate out calcium and barium? So basically, right, what is even insoluble? And then you're kind of looking for something, right, with a large difference in order of magnitude. And you can think back to what we did in class, so let's just kind of refresh our memory. And so previously we were looking at magnesium and calcium and hydroxide and how that's separated out. And so if we look at the chart, let's put in perspective their order of magnitude difference. So we said calcium hydroxide, so that's 10 to the negative 6 versus magnesium hydroxide. So that's 10 to the negative 13. And so now comparing barium and calcium compounds, what are some options that we have, and then what might be the best ones? See, so I think I heard, so you said either barium fluoride or calcium fluoride. So that could be interesting. Or you said sulfate was our other option, so let's compare. Or we could look at, so barium sulfate, where's calcium sulfate? So now this is kind of interesting. So we have barium sulfate is a lot less soluble as the sulfate versus calcium is a lot less soluble for the fluoride. But I would say both of these are pretty appropriate. And so I think both of them are good choices since they differ both by about 5 orders of magnitude. So really no difference there. And then you're not given too much other information, so we want to separate calcium from barium by selective precipitation. It doesn't really say like which one we might want to precipitate first. So I would say either choice would work with that case. I think the official key just says sulfate, but there's no reason why fluoride wouldn't be appropriate either. So does that kind of make sense, what you're looking for at least? Some sort of difference in magnitude. And let's see, I'm trying to see if there's one that like wouldn't work as well, but. You know, you could argue that maybe the carbonates don't work. Like, let's say if we were comparing calcium carbonate to, we'll look at magnesium again. That might be a little dicier, and the only reason I'm saying that is because we have 10 to the minus 9 and 10 to the minus 6 there. So that's still 3 orders of magnitude, but it's kind of close. So then, we'd have to do a little bit of math like we had done over here to figure out, well, how much of your other ion will be present as the other is precipitating out type of deal. Yeah. So the further apart they are, the better for separating. Because that just means that there'll be less of that other ion as the other one is precipitating out. And so that one I'll put either sulfate or fluoride, since both about 5 orders of magnitude different. Did you want to look at the other ones like that? So now do the same for iron 2 and iron 3. So how could we separate them? I'll flip back to the chart. We might need, let me try to pull up, I think we might need the book chart for this one. Sorry, I'm still trying to load your book chart. There we go. Scroll around too. Well, first of all, I see one issue already, is that we don't have too many options now, do we?
Carbonates and hydroxides and sulfides, and 1 sulfide. Are there any of these?
Yeah, so sulfides doesn't really work because they only gave us iron 2, so we don't have iron 3. We would have to go look up the solubility. But let's see, what are our other options? So carbonates, but same thing, so we just have 1 iron there.
Yeah, it's a -6.
I think it's
No, 11. Oops.
the oxidation state, though, is 2+. So.
I meant the timestamp.
Oh, yeah, but we need to compare it to something. So then that kind of leaves us, it looks like with only this option, at least to compare from this chart. So obviously, if you were in your own research group or whatever, you could be looking up, iron 3 versus iron 2 sulfide, maybe that would work. But just given our book and our options, we'll we're comparing iron 2 versus iron 3 hydroxide. And conveniently, what do you notice about that difference in order of magnitude?
It's ridiculous.
Yeah, so it's pretty large. And so that seems like the best route then. And again, they didn't show us any other iron 3 compounds really to compare. But so based off of our book options, we can say hydroxide is the best choice. And so we could say something, again, you want to emphasize a very large difference. So one's 10 to the minus 17 and the other is minus 39. So large difference. And then let's try this last one. So what cation could we use to separate carbonate from oxalate by selective precipitation? Let's see, I think we got to look back at your book one for this one. So there are oxalates. Trying to show all the oxalates and carbonates. So anything stick out? This is another one where there's like not too many options. So we, in, oh, strontium. SB is antimony. But yeah, I think you're correct. And so this is one of those ones where I would just examine. So you only have 4 oxalates, unfortunately, to choose from based off of this chart. But if you look at silver, well, this is minus 12. Compare the carbonates, it's also minus 12, so not a good choice. Calcium, minus 9. Carbonate, also minus 9. Magnesium, minus 7. Magnesium, minus 6. Not the greatest. And then strontium, minus 7. And then where'd the other strontium go? Strontium, minus 10. So still not the greatest in my opinion, but again, just given our options, that's probably the best one to choose from what we have. You know, you can say only 3 orders of magnitude difference. And again, if you were doing your own research lab, doing your own thing, you might want to find a better metal with a larger difference. So strontium, I'll just say only 3 orders of mag. So how are we feeling? Do we want to do either like 4 or 5, or would we rather do one of these concentration ones? Let's see. So do you want to do like 3 maybe? Calculate the KSP or this lead chromate species? All right, so let's try that. So calculate the KSP or lead chromate given its solubility. So I'll give everyone a few minutes to kind of work through it, and then we'll go over it. And so notice some funny things about how they gave you solubility. What is that equal to when we calculate it? So what's the first problem with this? And what do we usually calculate when we calculate solubility? Yeah.
We're doing it in moles per liter.
Yeah, so usually when we calculate, so, you know, we find our KSP or whatever, we're calculating our molar solubility. And they gave it to us in grams per liter. So the first step is to convert it back to molarity. So I don't know where we are in our steps. So I'll let people pluck away for a second. Oh, look at.
So when we do a grams per liter conversion to molarity, I just feel like I'm.
But you could also set it up right as dimensional analysis. So you want to go, you're in grams per liter, you want moles per liter, so you just need to go from grams to moles on top. So then how would you do that?
Find the molar weight, molar mass of our reagents.
Yeah, so we just need to find molar mass of our lead chromate. So I decided to be lazy and ask Google because I didn't feel like adding all those together. But then once you have the molecular weight, what do you do with it in our 1.7?
Just divide it.
Yep, so just divide, so right, we need to go grams to moles. So now we can divide, and that should give us our new molar solubility, so we can interpret that. And so now this is our molar solubility. Now, do you remember what to do with KSP? Yeah.
We take our molar solubility equation and just do algebra from there.
So you're right, but walk me through. So what do you mean by when you say take our molar solubility equation?
And we put 5.25 times 10 to the negative 7 equal to the root of n plus n KSP over n to the power of n to m times m to the power of n.
Oh, you plugged it into, yeah, that's, so how do we get there though without using the confusing m over m formula? Because I think what you said was right, it's just, I think, yeah, well, it's just, how do we get there simply? So we could use a formula, but let's just, right, think more simply. Set up your expression. So what's going on? So lead chromate, right, disassociates. Because what we need to get, and you know, what you were telling us with the formula is like, well, do we need to square things? Do we need to whatever? But for me, it's easier to just see it like this. So then I know, okay, well, I make one equivalent of lead and one equivalent of chromate. And so now we can plug in, and remember what our S molarity that we were calculating. So we said, right, however much solid, our molar solubility would be S and S. So then, right, this is equal to our molar solubility, which I think that's what you were getting at. And so now we just have to plug it in to our expression, again, like Vaughn was saying, except I think it's just easier to see we visualize this in our Rice method, and then we can see, well, our KSP is equal to my lead times my chromate, which is just S. So then KSP ends up being whatever we calculated for our molar solubility squared, since it's just times each other. And so then you just have to plug it into the calculator for your KSP. So I get like 2.76 times 10 to the negative 13 then for the KSP of this. So let's try that one more time just for 4, because that might have been a little confusing. And then, so note for 4, when you do this one, you have your 2 there that you have to account for. So walk me through how it's going or what y'all did. So what do we start with, Vaughn?
So first we have to convert our solubility to molar solubility, which I divided our grams per liter by a value by 461.01 grams per mole, which got me a molar solubility of 1.35 times 10 to the negative third.
And so I saw some nods, so everybody got this at least? Excellent.
And then, since that, we have a value, we get two iodines. We have to square it in our KSP. So we get 3.5 times 10 to the negative third.
But almost. So you do have to square it, but don't forget that you also have to double it in there.
Right.
So since, right, this S that we're calculating is really 2S. So we can plug this in for the value of lead, that's fine. This 1.35 times 10 to the negative third. But then before you square it, you also have to double it is the only tricky thing. And I think if you use the formula, I don't know if that, to me the formula honestly confuses me, the KSP one, but if you went back to the formula, that could help you understand it. So then you get this answer that you should plug in for iodine squared. It's 0.0027 squared, and then multiply it by the other answer. Oops. So then, do we get this for the KSP? Uh-oh. What do we get, or, so what happened? So if you didn't get there, did you get this for the iodine concentration? So did you double it? So double check that, so 1.35 times 10 to the negative 3 times 2 should give you 0.0027.
9.82 times 10 to the negative 12 is what I got.
Got it.
So let's see, what do we get? So people that got different answers. So what did you get for your value of iodine? So did you get 0.0027?
I think it's because for the molarity I got
0.0013?
Oh, basically, she rounded it up to 1.3 and left it super far in the weeds. I actually got a different answer because I went further and did 1.347 times 10 to the negative 3.
I feel like it shouldn't make that much. So then if I do times 2.6,
2.7, right?
I'm trying to calculate their value. So then if I use your 1.3, I think I get like 8.8 times 10 to the negative 9, which it's at least the negative 9 order of magnitude. Yeah, so your number shouldn't be so far off. So as long as you got something to the order of -9, that should look good. But hopefully you got close to this 9.8.
Oh, I see the algebra issue I made. Yep, there we go.
Excellent. All right. Other questions on the homework that we want to go over? All right. So calculate the equilibrium concentration of lead and sulfide and calculate the solubility, except now it's asking for it in grams per liter. So see if you can start that, and then let's see, where's lead? I think they have a different answer in the book. So lead sulfide.
Got it. 8 times 10 to the -28. Mole squared, or molarities.
So did we calculate our molar solubility at least?
It's the same as KSP.
Or, well, not the same as KSP, but just what we get, yeah, using our KSP. So then always start off with your equation. So S and S. So then just like we always do, so that just ends up being S squared. And so what do you get for the molar solubility?
2.82 × 10⁻⁴.
Yep, so that sounds good. I see nods. And so now what do we need to do? Just the last little bit. So they want it though in grams per liter. So how do we go now from molarity to grams per liter? Yeah, so multiply by, yep, and do you have the molecular weight of lead sulfide handy? 239.3, so grams per mole, moles canceled, so obviously this is moles per liter. And does someone have the answer plugged in? 6.8 times 10 to the negative 12th, and then again, that's grams per liter. Excellent. Questions about that one? This 4? All right, so let's look at this one. So give everyone at least a minute or so to get started.
Is 8. So that means that the Mg is going to come out first.
So let's kind of start walking through it together. So does anyone have the KSP values?
Yep. Zinc is 1.5 times 10 to the negative 10, and magnesium is 6.8 times 10 to the negative 6.
All right, perfect. So then looking at those values, so which salt is going to precipitate out first?
Magnesium will.
So look at that again. So remember, right, it's whichever one has the lower solubility is going to start to precipitate out first, since it's kind of least soluble. So then who goes first? So zinc. And so you just say zinc since it has a lower solubility. And so now let's try to answer the next question. And so it asks, well, what's the concentration of carbonate when the first salt begins to precipitate out? And so walk me through the setup. So what did you do for that one? What does that mean?
Soluble.
What values do I need? Exactly. So we care about the KSP of zinc first, since we want to answer the carbonate question. And then, so let's go back to our initial conditions, and it tells us that we have a 0.1 molar solution of both of these. And so that means we can set it equal to, so it's equal to 0.1, since that's our concentration of zinc. Now we just need to find carbonate. So what do you get when you plug this in? Exactly. So that looks good. And then, so now let's answer C. So now what's the carbonate when our second salt begins to precipitate? And so now we just use our KSP of our magnesium and still plugging in, right, the 0.1, because that was our concentration of magnesium as well. So now what's the carbonate concentration? Yeah, what'd you get when you plugged it in?
6.82 times 10 to the negative
4. Yeah. I also got negative. I got 10 to the negative 5 as well.
Yeah, that's what I meant.
Oh,
Did
sorry.
say
I thought.
fifth?
Yeah, sorry. You said 4. All right. So, excellent. So we all got to the negative 5. And so now I need this information. So now it's asking us, so what is the then magnesium 2 plus concentration when zinc begins to precipitate out? But then what we kind of need is the other condition, so the counter condition. So when zinc is precipitating out, right, the carbonate has this much concentration. So then based off of that, what's your magnesium 2 plus concentration? And what does that tell you? So plug in the number, see what it spits out, and then what the heck that means. So we're answering this question, but then what do you guys get when you plug it into your calculator? Yes, what'd you get?
And a very tiny number, 4.5 times 10 to the negative 15.
I double check that. Someone get. So 4,500, you said 33? So that sounds right, and it should be something ridiculous. I think you just entered something wrong on your calculator because it sounds like it multiplied by the negative 9 instead of dividing.
I forgot the references, that's probably it.
But then, so your calculator spits out this answer, but think about what this means in our starting conditions and kind of what it's saying. So what we're saying is, right, this is what the concentration of magnesium would have to be at these conditions. So when the zinc is precipitating out, we would have to have this concentration of magnesium for it to also be precipitating out. But then, what's our concentration, though, of magnesium to begin with? So 0.1.
So you need to have like what, an extremely minuscule amount of water, right? Like.
No, so this is kind of telling us how this separation is going to occur and kind of how effective it is in a lot of senses. Because, right, this is just what the math is telling us, but then we have to retranslate it and what that means, right? So it's saying what we're examining is the condition with which zinc is precipitating out at. So it's precipitating out when our carbonate is 1.5 times 10 to the negative fifth molarity, right? But then if we compare that to the solubility of our magnesium, and then y'all calculated, well, we would have to have this really high molarity for it to be actively precipitating, right? Because that's all that our equation tells us, whether it's precipitating or not. And so when it spits out that answer, that's saying, well, that nothing's happening. The magnesium is not precipitating. And so we're still starting with our 0.1 molarity from initially, and that's all that's going on, is the zinc is precipitating out and the magnesium is chilling. Yeah, question.
What about potential pockets of more concentrated
That
particles?
you're just assuming, yeah, homogeneous thing. You would not start calculating weird pockets. That's just not calculatable, like what you're saying. Right? We're just looking at our general homogeneous solution here.
I have to make a type of simulation to calculate things like that.
But then, so let's answer this next question, and it's kind of maybe more relevant. So then what is our zinc concentration when our magnesium carbonate begins to precipitate? And now you plug in
1.5.
Your carbonate that we calculated, right, when magnesium is precipitating. So this value. So now this is your carbonate value. What's the subsequent zinc value that would be related? And then plug that into the KSP, though, of zinc. (2.2 times 10 to the negative 6). So that sounds good. Did other people get that answer? And so, right, just the last bit for summary so we can think about this. And was this good? And so we're saying, right, we have 2.2 times 10 to the negative 6 left. We could plug that in. But basically, most of our zinc has precipitated out, so that's good, right? So now this is only a tiny amount left, 10 to the negative 6 molarity of zinc left in solution. Everything else has precipitated out, so you could calculate, right, your 0.1 molarity minus that, or do a percentage. So, right, 2.2 divided by our original molarity. And so basically, right, most of it has already come out of solution, You only have 0.0022% left, so I would say that's pretty negligible. And so, yes, that's a nice and effective solution, or precipitation then. All right, let's take our 10-minute break, and then we'll do our quiz. And I can also answer questions too about lab and all that good stuff. I will go ahead and stop the stream.